what to do. Write a little chart and look for least common multiple. I want the least common multiple of 35 and 42. The way to find it is to start writing multiples of 35 and multiples of 42 until you get to the one you want. Multiples of 35, the first one is 35. The next one? 70. And the next one? 105. For 42, it's 42. 84. 126. So far we haven't found anything common. We are looking for the least common multiple. Keep going.
You just add them together to get that.
No, I'm looking for multiples. I'm writing the multiples of 35. 35 times 1 is 35. 35 times 2 is 70. 35 times 3 is 105. 35 times 4? 140. 35 times 5? 175. Clearly, I'm just adding 35 every time, but these are the multiples of 35. I need to write the multiples of 42 as well. Don't wait for me. Write them down until you find the least common multiple. Keep going. And 26. 42 more makes 168. And 42 more makes 210. And 42 more, 252. And 35 more, 210. Now I could keep going and find more common multiples, but I'm interested in the least common multiple. This is a multiple of 35. This is also a multiple of 42, so it is a common multiple. I need to change my fraction by multiplying. What you're really doing is finding an equivalent fraction by multiplying the denominator and the numerator by the same number. Physically, this is like taking a pizza. If you have 3/4 of a pizza and you cut each one of those pieces in half, you end up with 6/8. You still have the same amount of pizza, you just have more pieces. I can cut it in half again, and I end up with 12/16. You still have the same amount, you're just changing how many pieces you have. So when I multiply this by what number?
6 and 5.
1, 2, 3, 4, 5. When I multiply 42 times 5, I get 210. But because I'm making more pieces, I also have to multiply the numerator by 5. And 11 over 42 is the same as 55 over 210. What do you multiply by the 35? Times 6. Whatever you multiply in the denominator, you also multiply in the numerator. Gives me what's called equivalent fractions. Same amount, just different number of pieces. This is 55 over 10. And 18 over 210. And I add my numerators. Do I add the denominators? No. Leave the denominators alone. You have a common denominator, 210. What's the numerator? 73. 73 is a prime number, so I'm done, because you can't factor it. You have no common factors. We would like to get a greatest common factor. It just happens to be 1, so you can't reduce it. That's the way you all learn to do fractions. Today I'm going to show you an entirely different process to follow. It is especially valuable when you have really big, ugly denominators. Can you all imagine that in some cases this could be very lengthy? If this number were, say, 175, and this number were 75, or 83, even worse, do you see that this could go on for a while? There is a method, however, that you do not need to find your common denominators first. You all see how I had to find the common denominator first? What if you didn't have to find it first? Wouldn't it make it easier? There is a method for this. Some of you have not learned this, so you're going to have to learn this new method. It is also used when you have algebraic fractions. We're going to call this one example A again. We're going to do the same problem. We're going to do it in an entirely different way, though. This time, instead of finding our common multiple, or least common denominator, we are going to factor our denominators. We're going to factor them all the way to primes. So some people will need a factor tree, some of you won't. Go ahead and write the tree for me. We're going to factor the denominators. Go ahead. Two numbers that give me 42?
6 and 7.
7 times 6. 7 is a prime, so I'm done there, but 6 can be factored some more. 3 times 2. Now what we usually do is write these in order. So 42 is the same as 2 times 3 times 7. We say that it's completely factored. We call that its prime factorization.
You want this one?
Smallest prime, well, you want prime factors. You factor until you can't factor anymore, right?
Why not do 2 and 20?
You can. You mean 2 and 21? Yeah. But then you get 3 and 7. You get 6. Yeah. 35? 5 times 7 and you're done. Because 5 times 7, both of them are primes. That is the prime factorization of 35. What I'm going to do, I'm going to rewrite this. 2 times 3 times 7. I'm going to write this one 5 times 7. In order to do this problem, I do not need to know what the common denominator is. Before I could do anything, didn't I have to know what it was? Okay, I want you to pretend we have no idea what it is. All I want you to do now is look at your denominators and multiply by what's missing. What does this one have that this one doesn't? Doesn't it have a 5 and this one doesn't? Now they both have 7s already, so that's okay. But this one is missing a 5, so I'm going to multiply by 5. And whatever I multiply in the denominator, I also multiply in the numerator. What's this one over here missing?
2.
2 and a 3, so I have to multiply by 2 and 3. Now you may have noticed something interesting. My denominators are the same. I have no idea what number they are, but I know that they are 2 times 3 times 5 times 7. Yes? And that's a really nice way to write your denominator because it makes it easier to simplify later. Because sometimes it's hard to find common factors, but if the thing's already factored for you, which it is, does everyone see that they're both the same? And they're both 2 times 3 times 5 times 7. And my numerators are 55 plus 18. Again, I add my numerators, and what do I get?
72.